Please welcome Joe.
Thank you. Appreciate it. Everybody hear me okay? Yeah. Good? All right, thank you. And thank you for inviting me and allowing me to come in and listen and get a chance here to talk about Altair Nano and really the market space too. I don't really want to make this about Altair more than questions from you about the market that I'm seeing as I travel and talk with different utilities and customers through the Western region, which is really my territory. Rob, I want to thank you for just mentioning our name a couple times in the bus, and we'll be talking about buses a little bit. And also I want to thank Charles, because Charles a couple years ago gave a talk on energy storage, and it really opened up my eyes. And I was like, wow, that's really interesting. And I talked to a bunch of my customers, and they were all very interested in it too. And how I came to fuel cell energy was from General Electric, and I lost a job to fuel cell energy up at Sierra Nevada Brewing Company. And Ken Grossman, the owner there, who I was trying to apply and had gotten pretty far with a Jenbacher generator, he was very concerned about efficiency and cleanliness. He said, look, Joe, I've got my brewery here that I built. I don't advertise. It's all word of mouth, and I really don't want negative connotations to my brewery. And I want something cleaner, because we were talking about SCRs and ammonia slip and concern from his neighbors on NOx. And I want to go with something cleaner. And when an opening came at Fuel Cell, I decided to take it, and it was a great meeting the people and the community that was part of that. So anyway, let's move over to Altair. I joined Altair about a year ago as they really wanted to make a push into the power sector to take the attributes of the batteries, which is high power, long cycle life, fast charge and discharge. Most batteries can discharge pretty quickly. It's the recharging of the batteries without without damaging or shortening their life. That's the real unique feature to the lithium titanate batteries. So we'll be talking primarily about the power sector, the grid sector, which is what this conference is about. I'll touch a little bit on the military and the transportation work that we're doing also. So Altair, just for a quick overview, we're headquartered up in Reno. We're actually a pretty old company. We're the material science arm of BHP, an Australian mining company, about 35, 40 years old. We actually had just a guy retire who spent 30 years with the company. Through various company reorganizations, they ended up selling off the R&D arm. We did contract R&D work and then went public as Altair Nano with the patents and the material science around lithium titanate oxide, LTO. And applying that in a couple of different ways. And we were looking at pharmaceuticals, we were looking at coatings, and we were looking at energy storage. And we really have stopped looking at pharmaceuticals. We've spun off to Sherwin-Williams. Just announced that a couple of months ago, any of the IP that we were working on with them, and have focused strictly now on energy storage for three primary sectors. The primary sectors are military, transportation, and then stationary power. Patented over the IP. The military, they like us for wide temperature range characteristics, fast charge, high power, long life. That fits also within the transportation sector. While we produce the powder commercially, through commercial production up in Reno, the cells are made in Korea. The cells then come to our manufacturing facility in Indiana, where we produce the battery modules and what you'll see later, the containers for doing stationary storage. So just a quick list of our customers here. Up on the top is what we've done so far in stationary power, and it may not look like a lot, but in reality that first unit, AES and PJM, that's been in commercial operation for over a year doing frequency regulation. It's the only battery system out there right now that's been doing frequency regulation commercially. And with the data that we've seen with that operation, where we are seeing that the life cycle of the batteries are proven out exactly as our cell testing has shown. Second unit with AES down in Texas doing frequency regulation, wind smoothing. And then some of the military work with ONR, they're looking at single generator operation, which is where they typically run 2 generators on board a ship and for reliability. Obviously, they're both running at 50% load or less, which isn't optimal for a gas turbine. They'd like to shut that down, reduce the wear on the extra turbine, and get a better efficiency out of the one that's running, and allow the batteries to carry on. We're also doing some work on weapon systems, once again from a wide temperature range, high power. And then what you see at the bottom third of the chart is the work we're doing with transportation, and really focused on mass transit, large bus scale like we saw with ISE. It's again sort of fitting the characteristics of the batteries. Long life, high cycle rate, high power, charge and discharge. Just to dig into the chemistry a little bit, and I'm not a chemist, but this gives a pretty good feel for the difference between different types of lithium batteries and a nanotitanate or a lithium titanate battery. And in particular is this LTO powder that we produce up in Reno, replacing the typical graphite anode with this LTO powder. And what that does, there's a few things. It increases the surface area by about 100 times on the anode side, allowing the lithium ions to migrate and charge much more quickly over to the anode. It also prevents the production of what's called a solid electrolyte interface layer right here. And that adds a resistive barrier and reduces the capacity of the barrier, creates more heat. And so those are kind of the characteristics that allow a faster charge rate, longer cycle life, and higher efficiency too. So that's just exactly what I said. So instantaneous high power charge discharge. When we talk about charge rates, we're talking charging up in less than 15 minutes. Our batteries can withstand a 6C rate, which means you can charge the battery in 10 minutes, fully charge it in 10 minutes. You can fully discharge it in 10 minutes also. Wider cell temperature range, excuse me, minus 40C to plus 55C without degrading the battery. A huge issue because, typically you're going to be abusing your batteries. That's what you want to help avoid. And if you do have to get stuck while it's cold or if it gets really hot, any kind of environmental concerns you may have, you don't want to have your battery shorten its life. So by having this wider operating range, you can have a much longer, more abuse-tolerant battery. Safer, we talked about safety, and actually Rob's slide pointed out it's one of the advantages of this chemistry is, you hear about lithium batteries, certainly everybody remembers the cell phones and laptops where you had thermal runaway that would occur. The operating window, safety window of these lithium titanate batteries, about 6 times wider than a standard lithium battery. That last bullet, it talks about cycle life, and I think that's where we go to with this chart here. So, and unfortunately this is a PDF of the presentation, or otherwise this would be more opaque. But what we're trying to show here is at 25 degrees C, you're looking at about 16,000 full depth of discharge, which is extremely high for batteries. Lead acids, somewhere around 1,000 or less. Other types of lithium batteries are in the mid thousands. So we're sitting around 16,000. This is 35 degrees C here, showing as you go up in temperature, you will drop down a little bit. That's around 12,000. And what was talked about earlier is you go to a shallower depth of discharge, and this is a logarithmic scale on the left-hand side. So you're starting out at 1,000 and going up to 10 million. And then a depth of discharge across the bottom, 100% depth of discharge. Once again, 16 and 12. And as you go to a shallower depth of discharge, you're starting to see cycles up around 1 million to above. And this is the range that we would expect to see occurring in a frequency regulation market, where you're just keeping that frequency, taking care of the transients on a power grid. And we expect to see 20 years of life. And what's been proven out with the project with AES is we've seen about 1% to 1.5% of degradation over the past year, which is exactly in line with what we would expect. Through cell testing and advanced cell testing, we talk about, well, what does that mean, end of life, or how many cycles? And what that means, it gets you to 80% capacity of the battery. Typically, after 80%, you see a knee where the battery drops off, and you lose a tremendous amount of capacity very quickly. What we're seeing with our accelerated life testing is that we're still going down linearly. So we're not going to go off a knee, but we're just going to go ahead and shallow out longer time. Of course, that's it's out there in the future here. But this is, in the past year, we've seen about 1.5% of degradation through the cycles. So the market that, from a stationary perspective, that we're attacking and we think has a great fit, and we're proven with the AES, is frequency regulation and renewable integration. Yes, sir.
I hate to ask a dumb question, but you know, everybody's talking over my head on this. This depth of discharge thing, and you're talking percentage. Can you explain to me why people just don't build, like, I mean, you've got a huge advantage of 100,000 at 10% and 10,000 at 30% based on your curve. Well,
almost. Well, let's.
Well, it says, I'm sorry, 1 million at 10 and 100,000 at 30. So 30 of what? And so in other words, you know, let's say I build a little bit bigger battery, I get 50,000 or 500,000 cycles instead of 100,000. You see what I'm saying? Is like how 30% of what? 10% of what? And why is it that you don't build?
I think that's a good question. I think that's a good question. So, you know, what we show with our batteries is that if you use the full length, let's say you have a, and I'll just, 100 kilowatt hour battery. Let's just, you know, it's for an easy number. If you take a 30% depth of discharge, you are going to go down to 70%. You used up 30%, so you've used up 30 kilowatt hours out of that battery. Okay, so that's 30% depth of discharge. You can go all the way down and pull 100 kilowatt hours out of it, and that'd be 100% depth of discharge. A lot of batteries, a lot of battery chemistry suffer life by going below 50% depth of discharge. So when you look at, you know, what's your usable headspace in a battery, that's sort of how you
well, I guess what I'm trying to get at is that when you have such a radical change across, I mean, you essentially have a logarithmic curve here. So if you got a battery that's twice as big, then you're only going to, and you're say at 20% versus 40%, then you've got an incredible increase in the number of cycles, but you've only doubled the size of the battery. And so I assume that's what we're talking about, is the volume of the battery.
So how I use this, right, in a competitive situation is I'll go in and say, well, what are you trying to do? Once again, we get back to the application. What's the power you want to pull out of this? Now I can, what I call, right size the battery to it, because I can use the full capacity of my battery. I was doing an example with the San Francisco PUC where they're looking at a NiCad battery. And the NiCad battery only had the top 30%, so they had to increase the size of their battery by double in order to fit that application. Took up a lot more space, cost them more money in the sense of batteries, but it wasn't, you know, I'm not saying my batteries are the lowest cost solution, right? But they're going to be a cost-effective solution. I was able to show them that with my battery chemistry, I can have a smaller footprint. You would still get all the amp hours for a longer life out of the battery. So that's how you use that to your advantage in a competitive situation.
Yes, and roughly what is the capacity of the battery? Roughly what is the capacity of the battery pack to get you into that desirable gray zone? You know, is it megawatt hour? Is it 10 megawatt hours?
Yeah, well, it depends on the application. So, I mean, what I can tell you is that the subset cells, the cells are for the power systems is a 50 amp hour cell. So, but I mean, it's not really germane to what you're asking. Depending on the application, right? Do I need a megawatt of power, and for how long? That would then dictate the size battery I'd have to put out there. If you needed 100 kilowatt hours, I would probably size my battery for 110 kilowatt hours, where somebody else may size their battery for 240 kilowatt hours. That way their depth of discharge would be shallower, so it wouldn't impact their life cycle.
Okay.
Yes, sir.
Yeah, real quick, and one answer to your question, Dan, is take a look at the Toyota Prius. That's precisely why their batteries do last so long.
I'm going to say the Honda Accord, which is what I have, and they barely touch the nickel metal hybrid. But anyway.
Is that because they're big?
So they'll last 150,000 miles.
So it's because they oversize them in the sense that they're not.
Well, I'd say less than oversizing. They took a much shallower depth of discharge out of them before they start up the engine.
I see. I got